Okay, the first one is the induction. So let us just recall it. So it says that so suppose Q is a set of integers such that so 1 belongs to Q and n belongs to Q. So this implies n plus 1 also belongs to Q. Then
Mm.
we can claim that for all integers
Mm.
greater than equals to 1, so that also belong to Q. So this is the basic thing, right? So I think this you already know, right?
Yeah, yeah. Wait, a principle listen. Okay. Yeah, yeah. We
Yes.
do it many times.
Yes. Yes. So the next is the well ordering principle. I think this one, yes, you have to recall.
Let me see again.
Yes. Okay. Okay. You want to say? Okay.
Uh, 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 yeah, yeah, yeah. Q here is
Yes, it is. It is not the whole integer set, but it is just a set of integers. It is not necessarily.
not set Q. Q is we
Yes.
have
Yes. That.
Q
Yes.
is
Yes. Rational number. It is not rational number. Yes.
okay, okay, okay. Not rational
It
number.
is. Yes. So rational number. The thing is we denote like this one extra line is there, right?
Ah,
Yes. So
I
that's why
is one. I is one. I
one.
one. Okay, okay, okay.
This is one.
Yeah, yeah. Okay.
Okay. So the next one is the well ordering principle.
Well ordering. Uh,
So the well ordering principle. So it says that so if A is a non-empty set of positive integers,
mm,
then A contains a smallest member. So it says that if it is a set of positive integers, we can actually order the set, right? So that is the idea.
mm,
Okay. So I think this is fine. So the definition is fine, right? Well, means this well ordering principle, the statement is fine, right?
mm. Yeah, yeah, yeah. If A is non-empty set of positive, then I contain a small number. We
Yes.
conclude that I must have a small lit.
Yes, it must have a small element.
So it's ordering.
Yes, yes. So the thing is, we can actually prove the induction. So the induction and the well ordering principle has a relation between them. So yes, that we can prove. So let us do that. So we can assume. Suppose let us take. So we'll prove that. So if mathematical induction holds, then the set has well ordering principle. So let us prove that. So the principle of mathematical induction. So we can state it as a theorem.
Mm.
So principle of mathematical induction holds if and only if well ordering principle holds. Right. So we'll prove like this.
What does it mean? Principle of induction.
Yes, yes. So the thing is, the principle
Oh.
of induction holds. Means it is true. If and only if the well ordering principle also holds. So suppose for a set, we can say that if the induction holds for a set, so that is we defined it. What does it mean that a induction to hold for a set? That if one belongs to Q, n belongs to Q implies n plus one belongs to Q. Then for all integers, it belongs to Q. So that is what we mean by the induction holds, right?
Hmm.
And we also know what is the well ordering principle. So the statement is, suppose the mathematical induction holds for a particular set of integer, so then the well ordering principle also holds. So that is what is we want to prove.
Mm. If we have principle of induction, that means everyone with the well ordering.
Yes, yes, it will also have the well ordering principle. Yes,
Okay, okay, okay.
right.
Mm, mm. But even though
So
I know about I understand about principle of induction, but
hmm.
why we introduce here? Yes.
No, I didn't understand your question. Tell again.
Mm-mm. Uh, in principle of induction,
Yes,
yeah, I can read. I can understand line by line, but
yes.
what does it mean? Why we mention it here?
No, no. The thing is that the well ordering principle is new to us, right? So the well ordering principle has a so we are the next theorem we have, right? So that is we are relating the well ordering principle for a set with mathematical induction. So that's why we are introducing this one.
Uh, yeah, yeah. Just theorem is it right? Yeah.
Yes, yes. So yes, some applications is also there because in a number theoretic proof also the induction also
Ah,
helps in the proofs of number theory. So that's why in the chapter they are introducing. So
okay.
induction is a very basic tool. So it is used in many J places.
Mm, mm, mm,
Yes. So we'll prove. So it is if and only condition. So we have to prove both sides. So first we'll assume that the mathematical induction is true, holds for a particular set, and then we'll prove. Means we prove that the set has a well-ordering property.
mm,
So we are proving this side, the forward direction. So suppose S is a non-empty set
mm,
of natural numbers, or that is natural numbers is same as the positive integers that has no smallest element. So we are doing by contradiction.
mm, mm,
So the by well-ordering principle, I know that it must have a smallest element, right? So we are doing by contradiction that it does not have a smallest element.
mm,
And let we create another set R. X belongs to that is the rational number such that X is less than equals to S for all elements in the capital S. So we
mm,
take all those natural numbers that is less
mm,
than equals to S for all the members of capital S.
mm,
Right now, since S does not have a smallest element,
mm,
have a smallest element, it is clear that the intersection between R and S that must be empty, right?
mm,
So suppose it was non-empty, then I can choose one element from R and that will be the smallest element in S, right?
mm, mm, mm.
Right.
Yeah,
Also,
yeah. Fair enough.
right. So also we can see that one belongs to R, right? Because since S is a non-empty set and one is the smallest element in the whole natural numbers, right? That is a positive integers, right?
Mm,
So since S does not have the non-empty set, R must contain that, right? Because one is less than equals to every positive integer, right?
mm,
So one belongs to R, and we assume that K belongs to R, right?
Mm.
So then, so any natural number that is less than or equal to
Mm.
this K must be also less than equals to S, right? So we are assuming K belongs to R means by definition, K is less than equals to S for every element of S, right? So
Mm.
between 1 and K, every integers, every natural numbers must be also less than equals to K, right?
Mm. Mm.
So less than equals to K must also be less than or equal to S.
Mm.
So for all S belongs to capitals. So this implies that 1, 2, up to all elements up to K, so that
Mm.
belongs to R. Okay.
Mm.
Now since the intersection is empty, R intersection S is empty, so these elements does not belongs to S. So
Mm.
1, 2 up to K. So
Mm.
these elements does not belongs to S, right?
Mm.
Now suppose K plus 1 belongs to S. So if K plus 1 belongs to S,
Mm.
then K plus 1 would be the smallest element, right? Because all the elements 1 to up to K does not belongs to S.
Mm.
So would be the smallest element, right?
Mm.
Smallest element of S. But that is a contradiction, right? Because
Mm.
S does not have any smallest element.
Mm.
So this implies that K plus 1 must also belongs to R,
Mm.
right? So what I showed that I assumed so 1 belongs to R, that I proved, and we
Mm.
assumed that K belongs to R. Then we proved that K plus 1 also belongs to R.
Mm.
Now we can apply the mathematical induction. So since we know that mathematical induction holds, so hence I am writing PMI, so that is principle of mathematical induction. R has to be the whole natural number, right? This R set is actually equals to the natural number set, because like that I can put entering every element into that set, right?
Mm.
But that will imply that S is an empty set, right? Because S intersection R is empty,
Mm. Mm.
right? But this is a contradiction, right? Because we
Mm.
started with S is a non-empty set.
Mm.
So
Mm.
but this is a contradiction. Since S is non-empty,
Mm.
right?
Mm. Mm.
So therefore, what you proved that every set of every non-empty subset of a natural number must have a smallest element.
Mm.
Therefore, the Royal ordering principle holds. Right? I think the proof is fine, right?
Yeah, yeah, yeah. I read this a little bit. Mm.
Yes.
This is- Mm. Mm. Mm.
Right.
Yeah, it's okay, but I
Yes.
put in the two line let S
Yes.
belong to N.
Yes. We are taking all those natural numbers. As
Later
that
than later than S.
no
So
less.
if intercept of S not equal to 5,
Mm.
Only in case of S equal to S is right.
Yes. No, no. The thing is, R. How we are defining R is we are taking all those elements from the
Yeah.
natural numbers such that it is less than equals to S for every S belongs to S.
So should be the less than upper bound
No,
less
R is a
than
set, right? R you cannot compare, right?
less than on element of S. That mean
Yes, yes, yes.
that
Every element of R
that's
is
mean I mean if here it S grid lesser than equal to S if I delete the equals sign.
yes,
So we always have intersect with S equal to 5, right?
yes, yes. That is fine. But we can keep the equality sign also. That is not a problem.
So the thing here we have the equal sign. So R intersect with S might not be 5. Is
Yes, yes. That is fine. But the thing is, this will make sure. Yes, this equality sign is not creating a problem because I know that S does not have a smallest element. So suppose the intersection is non-empty, right? Suppose there is an element that suppose an element is there. So Y belongs to suppose R intersection S, right? So Y belongs to R intersection S implies that Y by property of R, Y is less than equals to S for every element of S, right? So
uh,
this implies that Y is the smallest element in S, but that I know that is not true because we have assumed that S does not have a smallest element. So the
mm,
intersection cannot have any element. So this equality actually is not creating any problem.
It's okay. It's okay. No, not problem. But here,
Yes,
mm, mm, mm. Yeah, mm. Just confirm if the equal sign is not there.
yes,
So intersect with it always fine.
yes,
Even
yes. That is fine.
S have has a small element or not, is it
Yes,
right?
yes, that is fine. But the thing
Mm.
is, but
But
I have to.
we have the equal sign. So if
Yes,
S have a small element, intersect with it with should be the small element. But
yes,
here it's not so. So intersection with S should be 5. The 5.
yes. Because the thing is, why we are taking the equality sign is because I have to also produce that R is non-empty, right? Because suppose I
Mm,
give strict less than, and suppose S contain, suppose S is equal to N, right? Then I cannot. Then R is empty, right? Because I cannot even choose one belongs to R.
mm.
So that's why I need the equality sign.
Yeah, yeah, yeah. And we need to do this because if not this, we cannot conclude something like intersection with S
Yes,
because it's on Wi-Fi. It's right. Just
yes,
that, yeah, yeah. Small it even. My okay here. So actually, R and S should
yes.
have a common element. That's the smallest element, is right.
Yes, yes. Suppose so if RNS has some common element,
Mm.
then it will be the smallest element. Yes.
And the intersect set between them have only one element. That's the minimum.
No, no. The thing is, yes, the thing is, we cannot say that, but logically, yes, that will have one element. Means at least because we are claiming that the intersection is empty. For contradiction, we only need one element, right? So one element is sufficient.
Because here on S belong to capital S. That's
Right, right.
mean yeah. That's mean on S greater than S. So only one, I think so. Yeah. And
Yes.
on other is okay. Just that. Yeah. Yeah. Just this two sentence. Yeah. Yeah.
Fine.
Other is okay. Yeah. Yeah. Mm.
Right. So I think that is fine. So now we have to prove the other direction. So the other direction is we'll assume that the well ordering principle is true, and then we have to show that the induction works. Right.
Mm.
So that is the other part, the backward direction. So we are taking that let S be a set of natural numbers. Such that 1 belongs to S, and for any k that is greater than equals to 1, if k belongs to S, then k plus 1 also belongs to S. Right. Now, what we have to prove? The induction statement says that if this is true, then n has to be then S has to be n, right?
Mm.
Because like this, if we go along, S will be actually equals to n.
Mm.
So that is the contradiction. We'll assume
Mm.
that suppose that S is not equals to the natural number,
Mm.
then S bar, that is the complement, it is nothing but n minus S, that is non-empty because S is not the whole natural numbers, right?
Mm.
Now we can apply the principle of the dual ordering principle. So now using the well ordering principle, so what we have that S bar has a smallest element, right? That is what it says, right? Since it is a non-empty set of natural numbers or positive integers, I can say that it has a smallest element, right?
Mm.
Say Z. So suppose Z is the smallest element. Now, since 1 belongs to S, 1 cannot belong to the complement. So this implies that Z must be at least 2, right?
Mm. Mm.
So this implies that Z minus 1 is greater than equals to 1.
Mm.
So this implies since Z is the smallest anyway, so the minimality of Z, so the minimality of Z implies that Z minus 1 cannot belongs to the complement of S, right?
Mm.
So this implies that Z minus 1 must belongs to S because we are taking the complement, right?
Mm.
But by this condition of by so this is the first condition you can say, and this is the second condition. So by the second condition, we know that if Z minus 1 belongs to S, so this must imply that Z minus 1 plus 1 also belongs to S, right? But that is nothing but Z belongs to S. But this is a contradiction, right? Because we have taken that Z belongs to S prime or
Mm.
complement. So which is a contradiction since Z belongs to S complement. So we have assumed that the induction uh, induction. So we have assumed that S is not equals to n. So this is a contradiction. So his S has to be n, and the induction result is true.
Mm. Premise.
Fine.
Premise. Mm. So we have ordering.
Right.
Well,
We yes, we
ordering.
are assuming
Yeah.
that the well ordering principle is true.
True. Yeah. Well, ordering principle is true.
Yes, and we prove the induction.
So we have a minimum, the smallest value.
Right,
So here we take a set S such that we have I one equal to S. That's okay.
right,
What's number two for any k equal to one?
right.
If k belong to S, then k plus one belong to S. What
Yes, yes, yes. That is the
induction?
property. No,
Is
no,
it?
that is not induction. That is the hypothesis of the induction. So these two conditions. So the whole induction is up to this one. So the induction set. Suppose S is a set of natural numbers. One belongs to S, and this property hold that if K belongs to S, then K plus one also belongs to S. So this implies that S is actually equal to the natural number. So that is the whole induction. That is the induction principle, right?
Oh wait. One and two is how
The
how induction is right.
No, no, 1 and 2 is the hypothesis of the induction, and then by induction we conclude that S has to be equal to n, the whole natural number.
Okay. So we take okay. What we have to prove is well ordering and hypothesis of induction, and we want to conclude the consequence of induction. That mean S equal to n.
Right, right. Yes, that is
Uh,
what we want to prove.
okay, so we have three assumption here. One is well ordering principle whole,
Right.
and two assumption of
Induction of the hypothesis. Yes.
Okay, got it. Yeah,
Yes.
that's okay. So the next is yeah, mm, mm,
Right.
we use the contribution. So
Yes.
S not equal to n. Yeah, so complement of S. Yeah, S complement,
Yes.
not E5. Yeah,
Yes.
that's right. Mm. So
Now, since it is a non-empty set, then S complement must have a smallest element by the Euler ordering principle.
yeah, why well ordering, well ordering apply
S complement.
on S or S complement
Yes.
or
Yes.
S. Why we have well ordering? Mm,
Yes, we know that the well ordering principle is true, and that is applicable on any set, right? Now, since S complement is a non-empty set, I can apply the well ordering principle on S complement, right?
mm. So we just take the well ordering principle in the natural number only, is right?
Yes, yes, well ordering principle. Yes, so that is here is the statement, right? So it
Mm.
is a no is a non-empty for any set. There is a non-empty
Ah,
subset of
was
the positive integers is also natural numbers, right?
okay. So S and complement of S have small number. Uh,
Yes. So both are subsets of your natural numbers,
okay.
yes, but we are applying on S complement.
Okay. So we have Vicon is yet. Yeah. Mm.
Fine.
Yeah, okay, greater than one.
Right.
Yeah, greater than two. So greater than one. Yeah. So z minus to one. Z minus to one belong to S complement.
Right. Because Z is the smallest element, right? Z minus 1 cannot belong to S complement, right?
Mhm.
Okay, so this one is, I think, this
Not
does not belong.
not digital. Okay. You got this
I
fine.
think I told orally, but forgot to write down. Yes.
Yeah. Okay. That's okay. Yeah, right. Yeah, right. Yeah.
Okay.
So the number two. So z minus one belong to S. Z plus one belong to S. We put k equal to z minus one.
Right.
Oh, z minus 1 belong to it. Huh? Z minus 1.
So z minus one does not belongs to your s complement. So z minus one has to belong to s, right? Because both are
Ah, ah,
complement of each other.
okay, 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 okay. So z belong to both. That's the
Yes, that is a contradiction.
contradiction.
Yes.
Mm.
Right.
Mm. Mm.
Fine, right?
Yeah, yeah.
Okay. So one or two examples of a set for, and we can find the smallest element. So suppose if I take A to be the collection of all natural numbers,
Mm.
such that 3 divides n, right? So then the easy, right? So the smallest
Mm.
element is 3, right?
Mm.
Okay.
Mm.
Now suppose let us take another example. So B is the set. Is again n belongs to natural number, such that n equals to minus 11 plus 7m for some m.
Mm.
M belongs to integers. So can you find a small, can you find the smallest element of B? What will be the smallest element?
Why I in let's see three three because huh? uh
Yes.
three
Okay, let
three
me explain.
three why I I the first three
Yes. So we are taking all those natural numbers as a 3 divides n, right? So what is that collection? So it
given
is
three divide to n.
right. So this is
What
the
what is the notation?
yes. So this one is 3 divides n.
Three division.
Yes, yes. Okay, let me write down in English. 1 minute.
That's mean divide.
Yeah, right. Right.
Yeah,
So 3 divides n.
divide n.
Right.
That's mean n divide. Okay, okay, okay. Modular something. Modular equal to zero is right.
Yes, yes. So yes. So that is n is 0 not 3.
Okay, okay, okay. Okay. So it's three, six, nine. Okay. That's okay.
Right. So this smallest element is 3. That is clear.
Yeah,
Uh,
yeah, yeah.
what
And,
about B?
b equal to n minus 11 plus 7 m for m equal to yes. Yes, is a fraction.
Z is the set of all integers, right? That is positive, negative, everything. That integer set.
Okay. Something forgotten. Okay, yes is the integer set.
Right.
Yeah, yeah, yeah. Z is the integer set and Q is fraction.
Yes, yes. Q is the rational numbers.
Okay. The next is what? QZ, QR.
Yes, yes.
But
R.
I think C, R, and another.
Yes, yes. So that is the relation is your natural
No, no,
number.
no. We have more one set. Just remind something.
Yes. So this one you are saying, right?
Okay. And what? Real number.
Yes.
No,
Real number. R
I
is
think real number equal to Q plus something is right because some boy we cannot notation such as 3/2. That's what.
yes, yes, yes.
For example,
That is the irrational number.
square root of 2. That's what's the
Irrational number. Irrational. Irrational numbers. Irrational number you are saying, right? That
irrational
is
number.
yes. That is root 2.
The notation of irrational number?
Irrational number there is not a standard notation. So we
Okay.
just use it as Q complement.
Okay, okay, okay. So Q is rational
Yes,
and
Q is rational.
rational and irrational. We have okay, okay, just that. Yeah, okay. So here is integer. So the integer include zero is right. Integer says include zero
Yes,
or not.
yes, it includes zero. But natural numbers,
Natural number include in zero or not?
no, no, it's starting from one, one, two, like
One.
this.
Sometimes confused from base system. Yeah. Okay. So does mean we have n greater than one. That's mean
No,
uh,
m belongs to integers. M can have zero, negative, everything. Z Z has all the things, right?
n and not m. I say n.
Oh yes,
M.
N, capital N. The natural number is one, two, like this.
Oh no no here n the small n. So small n should be greater than one. So 7m greater than tail.
Yes.
So
So the condition here will be
n greater than tail divide to
no.
7.
This is greater than zero, right?
Hmm?
This has to be greater than strictly greater than zero, right?
Oh, not one because n belong to n capital N from one.
Yes, yes. That is from one, right? So one.
So I greater and equal.
Yes, yes. Then
Uh,
it is fine.
yeah, yeah, okay, okay. I always forgot to. So tail divide to 7. That's the 1 by 7. Yeah. So n greater than 2 is right.
Yes. So m has to be greater than equals to two, right?
Mm. Yeah,
So that two is the smallest number, right?
yeah. 2 equals small number. Yeah.
No, two is for m. The choice of m is two. So then what will be n?
Okay. So that's the 3.
Three, right?
3.
So the smallest number is three,
Yeah, 3.
right? Let us do one more set. It is so this one is the set C is n belongs to natural numbers such that n equals to x square minus 8x plus 12 for some x belongs to the integers. Yes. So here also you have to find the
Mm.
smallest number.
Mm. Yeah, that's me. For some years. Yeah, yeah. We how to deal with it? I open the whiteboard.
Yes, yes. So here we can do. So the thing is, we have to factorize it. This is a quadratic equation. So I
Um,
have to find.
yeah, yeah. Yes. So for some, yeah.
Right. So x squared minus 8x plus 12. So this has to be strictly greater than 0, right?
Yeah. Greater than zero. So
Yes.
we
So you just
uh,
factorize and tell me. So it can be factorized, right? So
uh,
tell me what is the factorization.
so we take the solution of x is right. Is equal to zero. What is the solution?
Yes, yes, that
Yeah.
we need. So
Uh,
just tell me the factorization. So it can be written in like this form. That x minus a times x minus
minus
b, like
yeah,
this.
yeah, yeah. It's way. Uh, hmm? Wait a minute. Uh, maybe we yeah knew the delta.
Yes, yes, you can do that. That also you can do.
This is 2AB. 2AB. So B equal to 4. 2AB.
Okay.
Wait, this way. This, okay. So it's the six
Right.
and
One is 6 and another one is 2. Right.
one is one six and one two. Yeah,
Right.
one six and one two. Mm.
Right. So this has to be strictly greater than 0. So what is the domain? What is the domain of x?
So
So
we
this is the real line. Suppose.
realize we have two and six,
Right. 2 and 6. Suppose it is 0.
and
Then which part?
we have plus minus plus is right.
Yes. Yes. So this part.
This the right left hand side is the plus side.
Right.
Mm.
So this part is positive. Right.
Mm.
And this part is also positive. Right.
Positive. So it's a grid. It's will
Right. So we must have.
dry and phone and dry. Yeah. Mm.
Right. So this is the range. Right.
Mm.
So this is the thing. So then what is the smallest one, right? So since it is, so the nearest one is, so since we are trying to find the smallest one, so x is 7 or x is, sorry, x is 1 or x is 7. So this is the nearest one, right? So now for this we have to check which one is the minimum value, right? Which one offers the minimum value.
Zero where? Zero here. Okay, okay. Zero here. Greater than zero. Wait. Oh, I a little bit confused. So right and down and up, down, up. So two zero here, zero here. So greater than greater than six, greater than six. So
Right. So this part is, so
greater
this
than
part is
six,
positive
greater
and
than
this.
six is okay because it's zero in six and it's dry. So it's okay, but I don't have pencil. It's a little bit.
No, no. Tell me what is the doubt. So the thing is, we have to find the values of x where this whole quantity is positive, right?
I write in the bond like that is right.
Okay.
Two here and six here.
Okay.
So zero here. Zero here is right. No. Ah, what the so that is like that. That's a little bit confused. That's yeah, parabol is right.
Okay.
Parabol.
No,
Hmm?
actually, I cannot see your board because I think you have to give me access.
Okay, okay. Can you see the ball?
No, the thing is, you have to give access. I have opened the board, but you have to give access. I think I send you an email.
No, no. I open on the the communication you can see on the message
Yes, yes,
the message of
yes, yes. I got it. No, this also I opened. I clicked the clean, but you have to give me access. So it is there is access is denied.
yeah. Okay, okay. I'm not this. Yeah, yeah. So here we lesser than two. Uh,
Right.
Let
So the thing is, what I'm saying is, if x is less than 2 or it is greater than 6, it is positive, right? The product.
mm, mm.
So the thing is, since we want to find the smallest number, so it must either occur at x, because the nearest number that is less than 2 is 1, right? And the nearest natural number that is greater than 6 is 7. So either it will occur at 1 or it will occur at 7, right?
Later than 2. Later than 2. So 2 is the maximal.
No, at 2 it is 0. So 2 and 6 it will be 0, right? This thing.
And we here just the s, yeah, s equal to 1, y s equal to 1 because s less than 2.
Yes, yes. Since x less than 2, and we want to find the minimum, right? It's the smallest element, right? We want to find.
Mm. Okay, okay. We take the function. Yeah, yeah. Okay.
Right?
Mm.
So now we have to just calculate what is the values. So I think both of them is symmetric. So that's why I think. So suppose x equals to 1 if I put, then it is 1 square minus 8 times 1 plus 12. So I think that is 5, right? Also, if I do 7 square minus 8 into 7 plus 12, so that is also 5. So the smallest element is 5.
Mm.
Right?
I think we wrong some way because if it equal to 1, 1
Right.
minus 2 equal to minus 1. Okay. 1 minus 6 equal to 1. Okay.
Yes,
So
yes. The thing is, whenever it is less than 2, both
uh,
of the things are negative. So that's why the
uh,
product is becoming positive.
okay, okay. Okay, okay. What is, yeah, yeah, yeah. Yeah, okay.
Right?
Hmm. 1 also, yeah, smallest one is fine. Yeah,
Yes,
okay.
it is symmetric. So that's why.
Uh, uh, yeah, 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 yeah. Okay.
Right. So the yes. So the thing is, the well ordering principle is true for integers. Sorry, the natural numbers, but actually it is not true for the rational number, because the thing is, if we take any smallest element in the rational numbers, so then x minus 1, if x is the smallest element, then x minus 1 is also a rational number that is smaller than x. So that is a contradiction, right? So
Mm,
rational number we cannot have a smallest element. So
mm,
I will write down. So just one observation. So this Q is a set of rational numbers, is not well ordered, right? So suppose x is the smallest element, right? In Q. So then x minus 1. So this is also a rational number, right? Since x is a rational number. But this is x minus 1 is strictly smaller than x, right? So which contradicts the minimality of x, right? So this shows that q cannot have a smallest element. So q is not well ordered, right?
mm,
So I think this is fine, right?
mm,
Okay.
mm, mm. Yeah, yeah.
Okay. So yes, maybe we can stop here.